Hello everyone. So in the previous class we were studying about linear regression and we have solved for the equation of linear regression. Along with that, I did explain you the requirement assumptions for linear regression and the evaluation criteria for linear regression. Okay. So how things goes here in case of LR? You have been given y equal to beta naught plus beta 1x, where x is independent and y is a dependent variable. You are saying that the relationship between x and y is following this equation, where beta naught and beta 1 are coefficients. Okay, so in real data, real life data, real time data, whatever you want to say, you can. Just I'm talking about the data. Okay. We do have many problems which follow this equation. For example, you can say house price prediction, sales prediction. Okay. So industry, they are using for sales prediction, they are using linear regression as a predictive model. Why? Because there will be features present in their data which relates to investment on the products, and they are looking forward to know what would be the sales. So this is your simple linear regression which we have used to solve the entire cost function calculation. And you may have multiple linear regression too: beta naught plus beta 1 x1 plus beta 2 x2 and so on, where you are having many independent variables. Okay, value of beta naught and beta 1, these coefficients, actually, as I already told you, to identify these values which better fits in the equation is called training. Okay, so that's what you say as a training. I'm looking forward to identify beta naught and beta 1. Okay, and once you got these values, you put them into your equation, beta naught plus beta 1x. This is your prediction. Y dash is what you can predict. By giving a feature value, you can predict y dash. Okay, and how we got this thing? Just like by MSE, that is your cost function, that is summation of y p minus y ka whole square divided by n. Okay, we achieved the value of beta naught and beta 1 from this equation by performing optimization. That means I differentiated this equation with beta naught and beta 1. You know, I want to find the minima. The error should have to be minimum. For that, these parameters, what should be the optimal value? Where the error should have to be minimum, we did perform the partial differentiation, and that's how we got the value of beta naught and beta 1. I also told you that there are many criteria for evaluating model, linear regression model, like MSC, MAE, RMSE, then R2 and adjusted R2. I'm going to talk about them today. Okay, the preferred is MSE. Then I also explained you when to use MAE and when to use RMSE. In case if the value of MSC is more high, then you can calculate the root of it. If it is also looking more, then you can go ahead with MAE, absolute error. Because if the errors are more, their square will be more. So in that particular case, we can avoid MSC and we can have RMSC or MAE. Then R2 and adjusted R2, these two shows the variance of data. Now how they show? Let me explain you this thing also along with the quick summary of linear regression. This is what your expectation is. You can see a blue line, that is the standard line. For linear regression, your expectation is this. That means relationship between x1 and x2 should have to be linear. However, when you plot the points, you may get the points to be present here. You may get the points to be present here. You may get the points to be present here. Okay, so some points can be above, some points can be below, something like that. So they are errors. Okay, if all the points comes over the line, it may happen some come, and if all the comes over the line, then it is the best fit. Best fit. Okay, that means all the training points come over the line. Best fit. But it may produce an issue that is called as overfitting. Overfitting. And we don't want overfitting. Overfitting I already explained. That means while training the model scored very high, but while testing the model failed to capture the relationship. So in training it is showing that, oh, okay, I got every relationship. Perfect. But this may be due to what the assumption says, why the model got overfitted. The assumption says that there should be normal distribution in the data. Never forget the assumption for linear regression. There should be normal distribution. This is how the normal looks like. Okay, then residuals. The residual should also be normally distributed. Continuous feature should also be normally distributed. There should be linear relationship between x and y. Okay, linear relationship between x and y. Variance of residuals should be equal. That means that's called as homoscedasticity. That means variance, equal variance of residuals. Okay, fine. Let me share my entire screen. I guess you are unable to see the screen. Okay, that's good to ping me. Okay, that's good that you have pinged me right away. Now let me share my entire screen because when I was teaching in a flow, I forgot. Here I am. Summary. Okay, linear regression summary. Okay, fine. So I'm talking about the assumptions which I have already taught you. Okay, so normal distribution of the features, normal distribution of the residual, variance of residual should have to be equal. Okay, that means homoscedasticity. Okay, that's a complicated name whenever I pronounce it again and again. Is present when the noise of your model can be described as a random and the same throughout all the independent variables. Again, the mean of the residual is zero. I'm talking about the variance of residuals. If you if you plot residuals, what are residuals? Predicted minus actual, that is residual, that is error. So when you are going to plot the errors, its distribution should have to be equal. That is what we say, equal variance of residuals. And the mean should have to be 0. If you add E1, E2, E3, E4, it should be 0, then only the mean will be 0. Okay, fine. Then only it will be 0. All right. Then, here it is. See the distribution. This is the distribution of, this should have to be the distribution of the residuals. But this is hetero. The distribution is not same. You can see it is expanding here. The distribution should have to be uniform like this of the variance. Okay, fine. So what are the assumptions which we have studied in linear regression? Before applying the model, you have to follow these things: normal distribution of continuous features along with the residuals also. But however, don't be too much into the depth. Normal distribution of features, continuous features, is okay. If they are not normally distributed, apply log transformation, or square root will also work. Either log or either square root will work. Okay. Correlation, collinearity should not have to be there. Correlation, collinearity should not. Because of correlation, collinearity, your model will be overfitted, and it will initially show a best fit line. However, that will be an overfitted model. It should not have to be there. So these are something mandatory. Relationship between x and y should have to be linear. Variance का भी just बोला, the things which I told about the variance, that the distribution should have to be uh, like same, and the mean should have to be 0. Okay, if we can take these three things on priority. These are the priority assumption. Okay, then rest you can keep on side. All right, and you can apply linear regression model. Okay, fine. So yes, I have explained the requirements. I have explained you the errors also, and I want to talk you about R2 and adjusted R2. Okay, here are some templates I will share because today I got the query, so I will share all these notes with you all. Okay, fine. Huh. R2 R2 score. What is R2 score? See, R2 score is inversely related to MSC and directly related to RMSC. Lower MSC or RMSC correspond to higher R2 score, indicating a better fit of the model on the data. What it is saying, sir, there's a confusion, sir, here. R2 score, you told that variance, data variance, na? That's what it's correctly mentioned here. Variability of the data. R2 score is variability of the data. Okay. So if the data has high variability, R2 score tends to be lower, and vice versa. If the variability is less, then the R2 score will be more. How we can identify this thing? See, R2 measure how well your model explain the variation in the target variable. Okay, variance explained. Variance explained. What is variance? In statistics, variance is x minus x bar. That means deviation of a point from its mean. That is what a variance is explained. in terms of statistics. So it tells what percentage of the target variable variance is explained by the independent variable feature. There are the value of R2 lies between 0 to 1. 0 means the model doesn't explain the target at all. R2 equal to 1 means the model perfectly explains the target. How I can say explanation? What's the understanding of explanation? Okay, I am having R2 and all these things, R1 adjusted. Sorry, all these things I am having. Let me focus more upon this particular concept. Explanation of variance. What does it mean? It told that R2 is having the range 0 to 1. 0 means model doesn't explain about the target. 1 means it explain about the target. Okay, this one is good. Now, how this explanation can be expressed related to the target. You will be What you do is you make a plot of target. Okay, because features are contributing to the target. Okay, target and feature. Let's say target and the feature. How much features contribute to target? That's what it means to be variance explanation. Okay, it tells what percentage of the target variable variance is explained by the independent variables. Independent variables should be responsible for prediction of the target. I need to find the value of y. X, the features, they are responsible for finding the value of y. So how much they are, what percentage they are contributing, what percentage of the target variable is explained, its variance is explained by the features, that is defined by R2 square. Sometimes it happens that you get negative R2 also when you are not working on your data pre-processing is worse. And if you have done correct also, you got less R2, or sometimes negative also, model is worse. That means the predicting the average of the target values, then just predicting the target of the average of the target values. It's just predicting the average, nothing else. So if the features are good enough in calculating the target, then obviously R2 will be high. If the features are not well enough to predict the value of target, then R2 will be less. Again, try to connect with the statement which is mentioned above. R2 is inversely related to MSC. That means if error is more, R2 is less. Error is more means if the model is making more error, it is difficult for the features to predict the target correct. Difficult. If error is more, it is difficult for the features to identify the target, because target will be somewhat away from the actual. Error is more means predicted minus y is equal to error, and error is more. Okay. However, if error is less, R2 is more. Why? If the error is less, that means y predicted and y actual are certainly closer to each other. That means the contribution of my features are well enough in identifying the target. Okay. And if the data has high variability means what does it mean? The data is high variability. That means the points are unfairly distributed. Here, high variance. That means the points are very much far away. That's the reason error is more, because this is your best fit line and the points are having high variance. They are very much away. Because they are very much away, we are having so much error. But if the variance is less, that means points are closer. Closer, error is less. Error is less, variance is okay. Variance less, features are able to define the target. But if variance is high, error is more, and we do calculate the error from the best fit line. We do calculate the error from that. In that particular case, you will be having a poor model. You may have asked, you will be asked a question. Kindly explain the evaluation criteria of regression. You will be having MSC, you will be having RMSC, you will be having MAE. What are the difference between them? When to use when? This could be the question. When to use when? Okay, then the question will come R2. You will be asked a question. What is R2? What is the formula for R2? Okay, let's check the formula also. Let me show you the formula of R2. The formula for R2 is 1 minus sum of squared residuals. Okay, so 1 minus sum of squared residuals divided by total sum of squares. What does it mean? Sum of squared residuals. What are residuals? These are the errors. So e1 square plus e2 square plus e3 square, sum of the squares of the errors divided by total sum of squares is the total variation in the target variable and its average. Total variation in the target variable around its average. So you calculate okay, total variation in the target. How we can define total variation in the target? What is total variation in the target? Yes, total variation. That means, are you taking target variable points? Like, let us suppose this is yp. So the points in yp are y1, y2, y3, y4, all. So you are going to take the average of this thing. Let us suppose you are having n points. So average will be summation of yi by n. So what it is saying, total sum of squares, that is the total variation in the target. Variation in the target means y1 minus y bar, y2 minus y bar, y3 minus y bar. This is the variance now. Point minus mean is the variation. So total variation in the target around its average, obviously अराउंड एवरेज ही तो होता है, वो एवरेज ही तो लेना पड़ेगा, मीन हो या एवरेज हो, is the total variation. So are we taking the square sum like this, y2 minus y bar का square plus y3 minus y bar का square and so on? Total sum of square, that means that only, that means this thing is like in form of this equation. So total sum of squares. So that we call as a total variation in the target variable. So errors sum of the residuals divided by total sum of square 1 minus, that is R2. Okay, that is R2. And now how this goes. Understand what you are saying, 1 minus summation of errors ka square divided by summation of yi minus y bar ka square, that is your R2. If this quantity is more, if this quantity is more, then what will happen? If this denominator is more, what does it means? What it means? It's a variance, no? It's a variance. Okay. So if variance is okay, variance and this is the error, and there is a trade-off between bias and a variance. That's also I explained. Bias versus variance. There is a trade-off between these two. If variance is more, bias is less. If bias is more, variance is less. So if error will become more, variance will get less. There's a trade-off between. So if error is more, variance is less, overall this value will be more. Overall this value will be more. And if I subtract 1 minus more, the answer will come less. It means R2 is less. However, now again there is a twist. If variance is high, not that much high, variance error is less. If error is less, variance is high, but not that much high. Okay, so this ratio will 1 minus, this ratio will become minimum, because that's the ratio now, it will become minimum. So now here the value will be more, 1 minus minimum is more, like zero point 0.8, zero point 0.9, something like that. So here R2 is more, here R2 is more. Okay, but we do not have to make like this variance should be very high. No, variance should be very high. That will okay, because we have already studied here. Okay, we have already studied in the above point that the R2 measure also how well the regression model explain the variation of the target, tells what percentage of target variable variance is explained. And above also I told one thing, if the data has high variance, R2 tends to be lower. But right now applying the formula here, if the variance is high, if the variance is high, according to the formula, if variance is high, so this ratio will become less, and this ratio will become less. R2 is getting more, but you are saying that R2 is less. ये contradictory हो गया. This is contradiction. This is a contradiction. How you can say this thing if you are applying a formula in this particular way? If you're writing a formula like this, 1 minus squared residuals, you are the total sum of squares. Total sum of squares, you are talking about total variation in the target variable around its average. So this is the variance of the target. That means the points are spread, and if the points are spread, we said error should have to be more. But bias and the variance, error is the bias, and they are in trade-off between each other. If the bias is more, variance is less, and if variance is more, bias is less. There's a trade-off between these two. Okay. However, this particular case, what you have to understand related to R2, because R2 explanation, R2 score explanation, not everyone goes into this much depth. Not everyone. The only thing, okay, basic percentage of variance explained of target y y predicted. Formula 1 minus error का summation का square, that's what it said. Sum of squared residuals, so summation of ei square divided by divided by total sum of squares, that is total variation in the target around its average. The formula, as I told, that means sum of variance का square summation, y minus y bar is variance only. Okay, so I'm just replacing it with variance. So if this ratio is high, R2 is low. If this ratio is low, R2 is high. And how it will be low? How it will be low? If the variance explained is more, if the variance explained is more, error is less, then only it will be high. If the variance explained is less, error is high, then this will be low. Again, variance explained. Variance explained. What it is? Variance explained. What it is? X and Y. Okay, we told that variance explained means Y minus Y bar, and that is related to your predicted. That is your predicted. So this is your predicted YP. We are talking about the variance of this prediction. That's what it is. YP minus Y bar. How they will explain its variance? How? The answer is why not? Why not they will explain? The predictions are beta naught plus beta 1x. Okay, these are the predictions. Beta naught plus beta 1x. Okay, we expect linear relationship between these two. Okay, so there is a linear relationship between these two. How much linear relationship? How much they are related with y? That means how much x are contributing in the prediction of y. That is what they are saying variance explained. If the features x are having good contribution in the y prediction, variance explained will be more, r2 will be more. We are having a better fit line. Okay, again, there are many things in correspond to that, many things, and we have to understand technically. I just focusing upon this r2 only, and saying a square r2 r square, some there are these terms are being said r square. So now let me change the color. Okay, here it is. Let me change the color. Huh. This one again. If it is high, then obviously good R2 score you are getting. You're done with the model. Accept the model. There will be errors. It's not like that error will become zero. No, there will be errors. Error will not become zero. There will be errors. Sometimes the variance is this variance is very high. Error is very less. So it tends to zero. So R2 comes 1. That means all points are fitted. That means all points are expected to be fitted over this particular line. Expected to be fitted on this line. R2 1. Expected to be fitted over the line. It's not mandatory, they will. There might be errors. That means they might be present here or whatsoever. Okay, but expected. In our evaluation, we do want R2 score to be high, error to be less, MSC to be less. That's how they are inversely proportional. MSC is inversely proportional to R2. Okay, and it's clear also by seeing the equation. You can see R2 equal to 1 minus errors. Okay, this is residuals. Residuals is error ka square divided by variance ka square, summation of variance ka square. Okay, might be somehow what you think, sir. Error is MSC na, error ka square. So error or R2 to sir we are looking like directly. Okay, they are looking like directly, but that's not what we have to uh, wrongly interpret. That's not we have to talk as a wrong interpretation. No, that is totally wrong interpretation, because here we are talking about variance explanation, and here the error is y predicted minus y. That is what the error, residual. And here we are talking about variance explanation. Okay, so that's not the case. Entire concept of statistics is being used here. Let me talk more about the terms. There is adjusted R2 also, modifies R2 to account the number of features variables in the model. So n is the number of data points. P is the number of features present in the model. This is adjusted R2. It helps in preventing the overfitting by penalizing the addition of unnecessary features present in the data. And sometimes we do apply R2, adjusted R2 also. Okay, and the explanation says that for penalizing the additional unnecessary features present in the data, so adjusted R2. Okay, because it may happen like you are getting high scores, and that be due to the features which are related to or which are giving you overfitting. Okay, which are giving you overfitting, that means correlated collinear features are present in the data. So your model is overfitted, and you are getting high score. So you have to adjust the R2, and this is how you can adjust the R2 according to this formula: 1 minus R2 into n minus 1 divided by n minus p minus 1. Okay, that's what you can do. Okay, so adjusted R2 is a modified version of R2 that adjusts the number of independent variables in your model, and it penalizes adding more variables unless improve the model significantly. Add the penalty. Unlike R2, adjusted R2 will decrease if the additional variable doesn't contribute, doesn't explain the target. That's what variance explain. That's what I'm saying. How independent features are explaining target. Okay, there are many independent features. For example, if you build linear regression model, you will be taking in X. It may happen you may take 5 features, you may take 7, 8, or 10 features too, depends. All right, how these features are explaining target. And target explanation is not that you have to write something in words, write in words, no. Okay, how you are, that's what we say, na, explain, so you are writing, no. It tells about data points distribution, and and it's somehow what related to your MSC mean square. That means error should have to be less. If we are having less errors, we are having a good explanation. That means your model which you have prepared to predict y, because error is less, and you have trained your model for prediction, and it is having less error, so the prediction is good. That means your model is giving yp, that is good. That means the distribution of yp is around y. Okay, so if the distribution, the presence of yp points are around y points, that means actual and predicted, the presence of yp is around, or it may be overlapping to, may be near to y. In this particular case, you say good variance explained, high variance explained, high variance explained. But if the presence of yp is far away from the actual, then low variance explained. So I told, now you have to refer this error. Okay, this error, that is a residual, or the error is in context of yp minus y, and yp minus y bar is variance. This is variance of predicted. So whatever be the distribution of predicted, okay, this is your error. So if the error is less, that means yp and y are closer, error is less, and the variance of y is likely to be as the variance of y actual, you are getting good R2 score. That means the predicted points are closer to y. Also, they are closer to this distribution is closer to best fitted line. Okay, that means, see, understand what I'm trying to say. This is your actual. Let us suppose this is actual, this is predicted. If the actual and the predicted, the point is coming here, one point is coming here, one point is coming here, one point is coming, some are coming over the line. That means actual and the predicted, they are the same points, no error, and they are also catching the line. So the variance is also same, their error is zero. Here the error is zero. Here all the points error equal to zero because they are coming over the line. And also y predicted and y are same. Here y predicted and y are not same, they are having some errors. Okay, so if this is the case where y predicted and y bar, the variance of y bar p, this is the variance, and yp minus y yp minus y actual, this is residual or the error, this should have to be less. And the variance means variance, this is for predicted, and it should be likely to be same as y, likely to be same as y. So if this thing happens likely to be same as y was actual, your predicted is also likely to be y. That means the contributors x, they are in a good judgment. They are in a good judgment to predict y, R2 score. Okay, though I was not expecting that I will take this much time to explain R2, but explanation of R2 is not that much simple. It's not available readily. Just only talking, okay, the R2 lies between 0 to 1, it is a variance, and so, okay. So here there are some features are contributing to the Y. Adjusted R2 means if it happens that there is overfitting, then you have to adjust R2. Okay, fine. So I took a bit time to explain this explanation of R2. And what circumstances you can use RMSC versus MAE? So circumstances, as I already told, that if MSC is more, then you try RMSC. And if you think that RMSC is not been good enough, its value is also more, then apply MAE. MAE. The only thing is the presence of points where they are. If the error is more, those are in that particular case. If the error is very high, then MAE is preferred. If the error is high, MAE is preferred. Okay, so this is what the explanation of R2 and all these parameters. Now next will be like I'm going to talk about the hyperparameters of linear regression. One code I will be explaining, and then I will switch to lasso and ridge regression. Okay, that means how to use linear regression, then I will switch to lasso and the ridge regression. All right, fine, let me stop sharing. Let me